Good morning. In today's video, we are going to talk about the physical significance of the Gibbs energy. Okay. Now, in order to understand that, we are going to make use of the two available laws which we have studied, and that is the first law and the second law. And here I have started with writing their mathematical form. So the mathematical form of the first law is delta U equals Q plus W. Similarly, the mathematical form of the second law is Q reversible is equal to T delta S. Okay. Now, previously, when we were talking about work, we were only considering the pressure volume work or the work of expansion. Okay. Now, as I told you at that time also, work can be other than the work of expansion, or the work other than the pressure volume work also is possible. So now here we are going to talk about the other work other than the work of expansion. So you can see here I've written work as a sum of both the pressure volume work as well as the work that is not involving any pressure volume work. Or in other words, you can write it as work of expansion or work of non-expansion. And this non-expansion work is also called as the useful work or net work. Sometimes they also called as the non-mechanical work. Okay. So this is what we are going to see and try to relate it to the Gibbs free energy, and therefore would be able to understand the physical significance of the Gibbs energy, how it is useful for us in deciding the criteria of spontaneity, which we tried to just visualize in the previous video. Okay, so how do we proceed? So we'll take the first law of thermodynamics. So here you see delta U equals Q. Now I have told you we are considering work of both the expansion work as well as non-expansion work. So expansion work we know is equals to minus of P delta V. Work of non-expansion we don't know, so we write it as such. Okay. Then what we did, we simply brought this term here, so it becomes delta U plus P delta V equals Q plus work of non-expansion. So at constant temperature and pressure condition, we know previously, if you look into if you have gone through the previous videos, you know that delta U plus P delta V is nothing but equals to delta H when you are considering a condition of constant temperature and pressure. So it becomes delta H, which is equal to Q plus work of non-expansion. Now, if you are talking about the process to be reversible process, suppose this particular process that you're talking about at constant temperature and pressure, if it's a reversible process, in that case, you can use the second law of thermodynamics, where heat is related to the entropy as T into delta S. So it becomes delta H equals T delta S plus work of non-expansion. Okay. Now bringing this term here, it becomes delta H minus T delta S, which is equals to work of non-expansion. Now, if you remember the previous video, we found that the delta G under isothermal condition is related to delta H and entropy as delta H minus T delta S. So same thing we are going to do here. So here, when you bring it here, it becomes delta H minus T delta S. So at constant temperature, it is equal to delta G by definition. Okay, so now what do you see? Delta G is equals to work of non-expansion And oftentimes it is referred to more realizable terms or more understandable terms like useful work or net work. Okay, so rather than using non-expansion or non-mechanical work, it is better to use as subscript useful. Okay, work of useful or network. Okay, network that is obtained from the system. So that is what we see here. So you can see delta G equals W useful work that you can obtain from a system. Okay, now let us try to understand how this is of any meaning to us, how we can know that. Okay, to understand that, suppose if you think that the work is done by the system, okay, if system is able to do spontaneously some kind of work, okay, in that case, we know that whenever a system does the work done would be equals to negative. It would be negative quantity. So that means what you see a decrease in Gibbs energy, because if it becomes a negative quantity, you can know that delta G is having a decrease in value. That is, when it's moving from an initial state to a final state, there is a decrease happening, and that's why delta G is coming out to be a negative quantity. Okay, so what do you understand from this? For if the process is spontaneous, then what happens? The delta G value should be negative. Okay, so that is what we understand from this particular relationship. So for any spontaneous process, okay, we observe the decrease in Gibbs energy, or in other words, the delta G value would be negative. Another statement that we can write here is the decrease in Gibbs energy at constant temperature and pressure for a reversible process is equals to the maximum useful work done by the system. Okay, so the decrease that you see, the magnitude of decrease in Gibbs energy, which we observe under constant temperature and pressure, provided the process is reversible, is equal to the maximum useful work that we can obtain from a system. Okay, so that is the another way of understanding this particular thing. Another definition, which is actually a definition kind of used for Gibbs energy, is that Gibbs energy of a system is the maximum amount of energy available with it that can be converted to a useful work. Again, both of these statements are kind of same thing, but in another way it is said. So Gibbs energy of a system is the maximum amount of energy available with it that can be converted to useful work. So in other words, this useful work is what is giving the system or a process the spontaneity, the urge to spontaneity. Okay, so maximum useful work is available, and that would be more and more spontaneous. Okay, so that is the condition for spontaneity, that is delta G should be a negative value. So higher the decrease in the Gibbs energy, higher would be the maximum useful work that you can obtain from a system spontaneously. Okay, so that is the thing. That is the physical significance of this particular expression. That means whenever there is a decrease in Gibbs energy, you can expect the process to be spontaneous, and it will continue till you have the delta G equals 0. Okay, till that happens, the useful work will be remaining with the system, and the spontaneity will continue. Okay, so spontaneity is coming as a result of useful work that is present in the system. So unless this useful work becomes equal to 0, you will have the process running in the direction of spontaneity. Okay, and once this useful work becomes equal to 0, then you can expect delta G to be 0, and therefore you have the process coming under equilibrium. Okay, so I hope you understood what is the condition of spontaneity. Let me remind to you again. So till we have a useful work, there is a magnitude of useful work available, the spontaneity will continue. Okay, once this useful work becomes equal to 0, the spontaneity will stop, or the system comes in equilibrium. Okay, so that is the basic condition for spontaneity which we come across. Now here we are only talking about system. We are not talking about surrounding. However, when you talked about the entropy as a criteria, you talked about system plus surrounding. Okay, but when you're talking about Gibbs energy, we are only talking in terms of the system. So that itself is an advantage, and that is why Gibbs energy is more kind of a final criteria that you can think of, which could give you a better understanding about a process or a reaction to be spontaneous or non-spontaneous. Thank you. Have a nice day.